Limits are a valuable addition to the mathematical spectrum of calculus because calculus is used to define numbers and concepts that can't be measured using real numbers. In physics, it is necessary to find the speed of an object at an exact moment in time. This is called the instantaneous velocity of the object. Using these equations, we can find the instantaneous velocity of an object, in this case an object in free fall. To find the velocity at 2.5 seconds, we basically go no distance and no time, but end up traveling at 24.4 meters per second. We can also use limits in terms of pi or e.
Limits are also valuable when there's a hole in a graph. Holes are tricky business, as no matter how many variations of the problem you use, you can never find the answer, unless you use a limit. By approaching the hole as closely as we can on both sides, we can estimate where the point would lie if it had existed.
A limit can sometimes be tricky to understand in instances like this. In this case, a limit cannot exist because f of x increases without a limit, so the closer you get to the limit, the higher your f of x value will go because you can never equal infinity.
Here's another instance when a limit cannot exist. It happens if one of these rules is broken. The limit of x as it is approached from the left exists. The limit of x as it is approached from the right exists. They are the same. If these are broken, it means that there is no limit of x.
The final time that the limit of x doesn't exist is when the value of x oscillates between 2 points as it nears the hole.
Limits aren't defined by what the actual point of the limit is because oftentimes the actual point doesn't exist. When the point does exist, the actual limit and the point can be manipulated as equivalent values. The same works for the idea of composite functions and of trigonometric functions when the limit can be substituted.
First, to realize you need to solve for a limit, you have to find what is called an intermediate function. This is when the bottom of the equation, when a limit is introduced, equals 0. This means that the limit cannot be solved by conventional methods, and a little sleight of hand is necessary. Always try direct substitution first. The ones that will work are mentioned in the theorems above. For those that won't, these strategies are commonly used.
The first strategy uses simplification. This can only be done when there is a common factor in the numerator and in the denominator. With a function that has a hole, by factoring out the x values that do not exist, you can find the same equation but without the hole. By plugging the limit into the limitless equation, you can infer and prove that the limit and the point have equivalent values.
The second
It is called the rationalizing technique. This can only be used on problems with rationals. By multiplying the reciprocal and simplifying, the new equation you create is equal to the first, save the holes. The limit can then be solved for easily.
The squeeze theorem is used to find a limit when the limit does not exist. Two functions that have the same limit are used, one that is greater than the equation and one that is less than it. By using a similar domain, we can squeeze the unknown value out by identifying the limits of these two sandwiching equations.
The two special trigonometric functions are used to set up the equation for use in the squeeze theorem. The limit of sine x over x equals 1. The limit of 1 minus the cosine of x over x equals 0.
The definition of a continuous function means in the graph of the function there are no leaps, gaps,
asymptotes.
or holes in it. If the graph is one of those examples, the function is broken and therefore discontinuous at that specific point. The function is discontinuous if one of these three requirements aren't met. F of c is defined, the limit of f of x exists as x approaches c, and the limit of f of x equals f of c as x approaches c. A removable discontinuity means there will be a hole at a point, but f of x will still be defined. A non-removable discontinuity means there will be a hole, but no defined point of f of x.
A limit can only exist if both the right and left limits are equal to each other. Sometimes a function ends at a point in which you can only reach it by following one side of the function. For example, if you have a piecewise function where a function ends with a closed hole at x equals 0, and a new function starts with an open hole at x equals 0, the limit would exist at x equals 0 with respect to the right side of x equals 0. Anything left of the hole does not exist.
The intermediate value theorem is an existence theorem, meaning if you have a closed interval of a continuous function and you know the start and end point, you can assume that f of c will be some value between f of a to f of b. You may not know what the value of x is, but you know it exists. The intermediate value theorem uses the same ideology. If you're given a function that's continuous, such as f of x being 2x cubed plus x minus 2, in the closed interval of 0 to 1, you'd plug the end and start point in. 0 plus 0 minus 2 equals negative 2, 2 plus 1 minus 2 equals 1. Therefore, the range of the interval is negative 2 to 1. You can then assume that some value of f of c would equal 0 because that value exists between negative 2 and 1.
Some limits can become infinite. With this comes asymptotes, vertical and slant.
A vertical asymptote shows a function as it approaches negative or positive infinity. This happens when a function has a possibility of a 0 in the denominator, such as x minus 5 or any other similar problem.
A slant asymptote is when the value the function is approaching is not actually a value, but rather a function. Some slant asymptotes are just a linear equation like y equals x, but there are some that have a cubic slant.
Apsmatopes, apsmatopes, apsmatopes.